Hello everyone, myself Rushabh Khara. Me and my teammate Niket Mania will be presenting on our final project, that is a basic routing information protocol, which is also called as RIP. These are the main contents of our presentation: introduction, purpose, design, constraint, algorithm, code, example, and reference. We'll start with the introduction. So what is RIP? RIP is a routing information protocol which is used to route data packets by finding the best hop count. It is a fairly crude way of trying to determine the best path. So this routing information protocol works on the network layer of OSI model, and it uses the port 520. So here the hop count is simply the number of routers existing between the source and the destination in the network. A best route to reach a network can be considered as the one with least node count, and it is placed in the routing table. RIP prevents routing loops by limiting the number of hop allowed during a path from supply and destination. So maximum allowed hop counts in RIP is 15. We'll see the features of RIP. The updates of the network are exchanged periodically. So routing information are always broadcasted. It updates the routing information. In updates, full routing tables are sent. The router always trusts the routing information received from its neighbor. So more onto this, there are three types of timer in RIP. The first is update timer. So the update timer is set to 30 seconds. So when the router's configured sends their update, it sends every 30 seconds. The second timer is invalid timer, that is 180 seconds. So whenever any router gets disconnected, the neighbor router wait for 180 seconds to hear an update. And if there is not any update, the neighbor router mark that particular router as unreachable. And the third timer is flush timer. The timer is set to 240 seconds, that is 4 minutes. So whenever any router does not go up for 4 minutes, the neighbor router removes that particular route from the routing table. We in this project we have implemented the distance vector routing algorithm by using the C++ programming language in a network consisting of router interfaces and subnets. Additionally, the network should support packet transmission to either router interface or subnets. So here we have used a distance vector routing protocol based on the Bellman-Ford algorithm, which is based on RIP protocol. We'll see the design constraint. The Bellman-Ford algorithm's time complexity is O in bracket V into E, where V is number of the vertices in graph and E is the number of edges in the graph. We are performing a V step, and each step access all the edges in the graph, therefore increasing time complexity. So one thing that is important here is that the Bellman-Ford algorithm cannot handle undirected graphs that have negative weights. However, as long as there are no negative cycles, you can only process directed graphs with negative weights. So these are the system requirements. It needs any type of operating system with minimum Pentium processor or equivalent, 4 GB or more RAM, uh, code blocks IDE or any text editor, GNU, GCC, G++ compiler, and terminal command prompt. So thank you from my side, and now I'll hand over to Niket. He'll take from here.
Niket here, and I'll continue further with Bellman-Ford algorithm. So in a weighted graph, Bellman-Ford algorithm computes the shortest path from single source vertex to all other vertices, and also it can have the negative weights for the edges. The algorithm is basically divided in the three parts. So let's talk about the first step, that is initialize the weights. So Bellman-Ford algorithm takes a list of vertices, edge and source vertex. So the first step is the initialize distance from source to all other vertices as infinite, and the source vertex itself will have the weight of 0, and there will be an array that will contain the values of the vertices. So as you can see, we have assigned the vertices to infinity and the 0 for the source vertex. So in the next step, we have to find the shortest distance uh, by visiting the number of edges minus one time. So if the graph is having five vertices, then we have to visit these loop for the 4 time. And in the condition part, what we'll do is, if the distance of v, that is I talked about in the first tab, is that if that is greater than the distance of u, that u is the u and v, yeah, u and v are the source and destination, consider it as a source and destination, and there is an edge between them. So if the distance of v is greater than the distance of u plus the weight on the edge uv, then we'll update the distance of v with the distance of u plus weight of the edge uv, and we'll do this. Let's say if we have five vertices, then we'll repeat this loop for 4 times. And the next step is it will only check for the negative cycles if there is any present in the graph, and it's also the same condition for the edge uv. If we'll check with, if there is a distance of v is greater than distance of u plus the weight of the edge uv, then we'll simply state that graph contains negative cycle. Here's the code that we have implemented from algorithm. We use the structure, and we have taken 800 that defines the infinity for our references. What we'll do is we'll navigate the for loop for the edges, and we'll do this for number of vertices minus one time. So if we have 3 vertices, we'll visit this for loop, outer for loop, for 2 times. And here we'll be checking the step 3 of the algorithm, that is to detect if there is any negative cycle present or not, and if there is any, we'll simply state that negative cycle detected. And this is the main function. Here what we'll do is we'll get the input from the runtime, and by iterating and calling the Bellman-Ford algorithm function, we'll get the output. So let me start with an example. So there's a graph given, and the source vertex is 1, and the rest 2 are the vertices that we need to find their distance, shortest distance. So we'll take the number of vertices as 3, the source vertex is 1, and there are 3 edge present. As you can see, it's a directed graph having the weights on the edges. So for edge 1, what we'll do is enter the source vertex as 1, the destination is 2, and the edge has weight 20. For edge 2, we are considering the vertices 2 and 3, so the source will be 3 and destination is 2, and having the weight minus 30. For edge 3, uh, source vertex is 1, the destination is 3, having the weight 40. So in the output, you can see the vertices number and distance of vertex from source. So 1 is source itself, so as per the algorithm, its shortest path will be 0. For second vertex, you can see there is a edge that is having the weight 20, but there's an alternate path also available via 3. So if we go to 1, 3 and 2, then the weights will be change for that will be 40 plus minus 30, so that will be 10, and the actual weight via the direct rows is 20, so the output will be updated for the vertex 2 and that will be 10, and for 30, and for third vertex we don't have any other edge, so there is no option to go, so that will be directly 40, and that's the example. These are the references that we have used to create this presentation. Thank you. That's it from our side.